Sir, good morning. Sir, mic off.
Okay. Good morning.
Yeah,
Good morning. Morning, sir.
Good morning,
Morning.
everybody.
Good morning, sir.
Good morning, Dr. Good morning to everybody.
Good morning.
गुड मॉर्निंग। सो बस अभी उधर से रघु का फोन आएगा, तो फिर अभी हमीरपुर का चल रहा कोई ना कोर्स, तो देन विल स्टार्ट।
Okay, sir.
ठीक।
Dr. Sunkaria, how are you?
Good morning. Fine, sir. Good morning, sir.
Good morning.
Good morning, sir.
Good morning, sir.
नमस्ते सर।
नमस्ते, कैसे हो?
फाइन सर, बढ़िया।
हाँ, शुरू कर रहे हैं हम लोग?
जी सर।
Well, so honorable director sir, Dr. N.K. Awasthi, chief guest of this inaugural session, head of the department Professor R.K. Sankaria, faculty colleagues, deans, dear participants, research scholars, ladies and gentlemen. I warm welcome to all of you in this short-term course on emerging trends and challenges in communication systems, which we are going to start here today. Well, if you'll see the history of communication, it is as long as the history of speech. As a human being, we started our journey, first of all, by writing the paintings and in the walls, in the caves, in the form of the pictures of animals and paintings of the stencils. At that time, it was used to communicate with the next generation. And gradually, we moved from there to the postcard, telegraph, and nowadays, it is the era of internet. And this STC itself is an example of that we are conducting this STC at NIT Jalandhar, and the people from different part of country, they are able to attend it. It all is because of the development in the field of communication system. But we cannot stop ourselves here. And this COVID-19 gave us this situation to explore more inside of the things that what more we can do in the field of communication systems. So, well, we are organizing this short-term course for all the researchers in the country to explore the new challenges and open field in which all we can give our inputs so that we can make the life of human being as a better as it can be. As the primary purpose of human being is to share and exchange the knowledges among all human beings, and the things science which is able to give us is this communication only, which I think is the best result of this 21st century. So, dear friends, my many eminent speakers from the Premier Institute will be the part, will be delivering the lecture in this short-term course. And I'm sure that if all of us will be benefited from all these lectures, whatever will be the lectures which we are going to organize in this short-term course. So once again, I heartily welcome all of you to attend this short-term course. So now I would like to invite Professor R.K. Sankaria, Head of the Department and Convener of this course, to please give a brief introduction of our Department, Electronics and Communication Engineering, NIT Jalandhar. Professor Sankaria, please.
Thank you, Dr. Satish. Good morning to all. The Honorable Director of our institute, Professor Lalit Kumar Awasthi, the chief guest on this inaugural function, invited experts, the participants, we, the faculty and staff of EC department, welcome you all on this 5-day self-sponsored short-term course on emerging trends and challenges in communication systems from 11th of January to 15th of January 2021. We congratulate the coordinators of this course, Dr. Satish, Dr. Sukhvinder, Dr. Pawan, Dr. Manjeet, and Dr. Nitesh for organizing this short-term course. Now about the Department of Electronics and Communication Engineering started its bachelor program in Electronics and Communication Engineering in 1989 with intake of 30 students. The department offers BTech program in Electronics and Communication Engineering, 2 master's program, one in MTech in EC, the other as MTech in VLSI design. The PhD, both in full-time as well as in part-time, is being offered in various areas such as biomedical signal and image processing, digital signal processing, its applications, VLSI design, emerging technologies, advanced communication systems, autism, antenna system design, microwave engineering, RF circuit design, etc. The placement in the department have been excellent and it has been more than 90%. The Honorable Director of our institute, Professor Lalit Kumar Awasthi, has always been supporting, encouraging and motivating us to take up innovative research works, contributing towards national development. The department has been actively involved in organizing workshops, short-term courses and conferences, with more than 20 short-term courses have been organized during COVID-19 lockdown. With more than 400 publications in reputed journals and conference, the department is very focused towards realizing the innovative ideas and novel research conforming to Government of India's Atmanirbhar Bharat campaign. Now we invite our Honorable Director, Professor Lalit Kumar Awasthi, the chief guest of this inaugural function, to say words of wisdom on this occasion. Thank you, sir.
Good morning and greetings from NIT Jalandhar. Dr. R.K. Sankaria, Dr. Satish Awasthi, Dr. Manjeet, Dr. Sukhvinder, Dr. Indu Sani, and deans, head of departments, and dear participants. It's my pleasure to be here on inaugural of the short-term course on emerging trends and challenges in communication system, organized by Department of EC, NIT Jalandhar. This institute is institute of national importance and came in 1987 as Regional Engineering College, Jalandhar. Now, as on date, we offer 11 undergraduate courses and 16 MTech programs and PhD in almost all disciplines of engineering, management, and sciences. The Department of Electronics Communication has been doing great, and during pandemic time, the faculty of the institute has published, I think, highest ever published publications in the history of NIT. So we have crossed 500 peer-reviewed publications. Congratulations to the faculty, and we have attained very good ranking in NRF, and again we have been ranked in top 4 or 5 institutions as far as digital literacy and teaching learning is concerned which has been conferred by DataQuest. This communication, actually, there are so many trends which are emerging, and there are so many challenges as well. We're looking for more and more speed, isn't it? Communication is all speed, about speed. So if you think of, if you're lucky enough to be there in 2G, 3G, 4G, then you can see now there is a 5G. So the people might have been thinking of 6G and things like that. As a student, as a teacher, or as a user of internet, you always look for your file. Oh, it is saying another 1 minute. So at time, there was a time when you start a download, they'll say, oh, it'll take 15 minutes, 20 minutes when you were in 2G. So you can think of the we are having so many advancements, and the speed is going high, but still the applications which we are running, they are forcing us to go higher. So we are looking for the applications where patient data can be given directly to the to be maybe a robot surgeon who is doing the surgery. So from a remote, it can be guided by the set of doctors to multiple sites. So a real-time communication is on one side, and the other side, which forces that the speed should be increasing. And there are other similar applications you have nowadays. Wearable watches where all data is transferred, and you have track suits which can get your data, can tell you that instead of jogging, you need to take rest and things like that. So many applications, and everywhere the pressure is on communication, that the communication, the different wearable devices, they need to communicate within a city. You may be connected to different locations, and when you want to start, you want that which best path you should take to office. All those things are centered in the communication range, and I hope that this particular program will be able to tell you about what are the latest trends. So not only in such courses we should talk of latest trends, but we should also bring in these trends to the textbooks, and we should be able to look into how these can be taught to the students. The students should be now, as on date, ready with the latest communication inputs. These words I congratulate Dr. Sunkaria, Dr. Satish Avasthi, and the team for taking this initiative of having this shorter course on communication system, and hope that everyone connected will be able to learn some good knowledge during this course. Thank you. Jai Hind, Jai Bharat.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
I invite Dr. Mamta Khosla. Welcome, ma'am. Now, it's my privilege to introduce you first keynote speaker, Dr. Abhay Kumar Shah from IIT Roorkee. Well, the topic in which Dr. Shah is delivering his talk is massive multi-input, multi-output, the key enabler for 5G and beyond 5G systems. I have also, let me introduce you make you with a brief introduction about Dr. Shah. Dr. Shah received his BTech degree in Electronics and Communication Engineering from JP Institute of Engineering and Technology, Guna. He received his PhD degree in Electrical Engineering Department from IIT Kanpur. After that, he worked as a R&D engineer in Samsung Institute, Bangalore, as a senior lead engineer from 2018 to September 2019. After that, he also worked in Red Systems India Private Limited, Bangalore, as a software architecture, where he was involved to develop various algorithms for 5G base stations. Currently, Dr. Shah is working in the Department of Electronics and Communication Engineering at IIT Roorkee as a faculty member. He has a lot of patents and publications in national and international journals like IEEE. So I want to come much between the participants and with Dr. Shah. So I again welcome Dr. Shah for this session, and I invite him to please share your talk with our participants. So Dr. Shah, please. Dr. Shah, you can share your screen, please, with our participants.
Sir, I think he's not able to.
Yeah.
He's not able to connect.
I'm just,
maybe. Yeah.
Maybe there may be some internet issue. I'm just calling to Dr. Shah. Yeah, please, there is some issue of connectivity with Dr. Shah. Very soon he will be connecting with us. We are just trying to connect him. Yeah, these are the real challenges which we need to address in coming futures in the theory of communication. This is a challenge for all of us, researchers, particularly the country like us.
Hello, am I audible now?
Yeah, hello, Dr. Shah. Yeah, thanks. Actually, now you are audible.
Yeah. Sorry for the. I guess I'm using Google Meet for the first time, so some permissions issue was there, so it was not working. Okay, so. Shall we start?
Yeah, Dr. Shah, please go ahead.
Okay. So let me just. Is my screen visible?
Yes, sir. It's visible.
Please.
Okay. Thank you, everyone. I would like to first thank Professor Lalit Avasthi and Professor Sankaria and Dr. Avasthi for inviting me for this talk. So this talk is Professor Lalit Avasthi already put up nicely that how communication has evolved, how it has started, and how we are moving towards very advanced or very futuristic, or you can say sci-fi kind of applications. So so this talk is all about achieving those dreams, and the one key aspect of that, the massive MIMO technology. So it is a key enabler for 5G and beyond 5G systems. So before starting the talk, I would like to just give a brief story about myself. So I am currently associated with IIT Roorkee and working as an assistant professor here. I did my PhD at IIT Kanpur, and since I joined my PhD in 2010, I am working on this field. So I have roughly around 10 years of experience in the field of massive MIMO. After my PhD, I worked at a leading R&D organization who works in the 5G domain, and especially towards the massive MIMO systems. I have almost more than 15 plus IEEE journals and conferences on the related field, and 9 plus patents on the related technology. This is I am in the center in this picture. So this was my first recognition at the international level, where I got chance to present my research work at IEEE Globecom in 2015. So in this talk, we first look into how massive MIMO, what is the motivation, why people go for massive MIMO, what is the information theoretic motivation, we will see that. Then we will get the answer a few questions, like what is the role of massive MIMO in 5G system, then when we are saying massive, what that does mean, what is the size, how big it will be, and there 5G supports several different kind of use cases. Does massive MIMO support all 5G use cases? We will see the answers of this question as well, and then we will talk about what is next. You might have heard of 5G is being realized. I already also told you that I was working in industry for development of 5G. So 5G is being realized. So what is next? What is the future of massive MIMO and how it will evolve with the future generation or the future release of 5G. Then we will conclude this presentation. So let's begin with, so since the inception of wireless communication, the one and only goal we have to improve the capacity. What we mean by capacity? So basically we want to improve our data rate. So so that you have heard of in kbps, mbps. So all how many bits we can transmit in a per unit time. So the first characterization of capacity was done by Shannon and this is a very renowned Shannon capacity expression, where it is a function of your bandwidth and your SNR. SNR is your signal to noise ratio, and this work it was done almost 70 years back. Although we started doing communication almost more than a century ago, but the first characterization happened around in 1948 and 1949, so that we are able to understand how the capacity of a wireless of a system like a medium behave in a with. So we found there are only two it is a function of only two variables. So if someone asks what can be done for improving the capacity, what we can do or how we should improve the capacity. So the two the natural answer is that since it's a function of two variables, that is a bandwidth and SNR, so we can simply either increase the value of bandwidth or SNR, and we will improve the capacity. So this is one plot. I have shown it here. So here you can see that if you increase the SNR, it is like the capacity increasing in a it's linearly it's increasing, but and capacity here it's for the per unit hertz. If you see the y-axis here, so bits per second per hertz. So so I would like to emphasize here that there are certain limitations with this approach, that we can increasing the bandwidth or signal power. So now let's say just focus here at 2 points, let's say 10 dB. Okay, sorry. Let's say this, your capacity at this point is 5, and the capacity at this point is around 10. So if you want to double the capacity, almost you have to double your SNR, around 15 to 30 dB. So doubling in a dB scale, basically if you go in the normal scale, it will be almost 100 times you have to increase the SNR. So these are and also you cannot increase the spectrum because spectrums are very scarce. So these two options, like increasing the spectrum or increasing the SNR, may not be viable options. So can we do something else? The natural question arises, can we do something else rather than only increasing the bandwidth or thinking of increasing the signal power so that we can increase the capacity? So the answer is yes. Okay, so what we can do, we can basically we can either improve the spectrum utilization, so that whatever is bandwidth we are using, if we can improve the spectrum utilization, we can increase the channel capacity, or we can increase the receiver SNR without increasing the signal power. Someone can ask how we will achieve these targets. So I'm not sure. Are you able to see the below part in this slide? Okay.
Yeah, Dr. Sai, you can hide that thing. Yes, now it's fine.
Now it's fine. Okay. So okay. So how we can achieve these these targets? So there are two approaches. One approach we known as diversity. So what we do in the diversity, basically we increase the number of independent paths between transmitter and receiver. So this is like you have one path here and one path here. So you have two paths from which your data can go to the receiver. So it is like creating a parallel roads or two different roads, so that you can send a same packet in two different paths, so that it can the probability of reaching to the receiver in a good quality improve. So what happens basically with this approach, your SNR at the receiver increases without increasing the signal power. So this is one fundamental fundamental approach. We can improve the signal to noise ratio at the receive side, that will lead to a better channel capacity. The second approach is the spatial multiplexing. So what we do in a spatial multiplexing, basically we transmit parallel data stream. So here, if you notice in the diversity case, we have same data which is being transmitted to two different antenna. Rather than doing this way, we can use multiple number of antenna to transmit parallel data. Like first antenna is transmitting some set of data, the second antenna is transmitting another set of data. So this basically helps us to improve the spectrum or bandwidth utilization. So these are the two different approaches, and which can lead to a better capacity. And the first characterization of this diversity in spatial multiplexing text happened done by Professor David Say and Professor Chang in 2000, early 2002, 2003, somewhere around. And these two concepts give us the basis for MIMO systems. Although MIMO was designed in around 94, but the first concrete analysis of how performance behaves with once we have more number of antenna or more number of receive antenna. So that has been done in around early 2000. So how? What about the capacity of MIMO system? So the results which channel has given for AWGN channel has been extended for a point-to-point MIMO system. Point to point means you have one transmitter, one receiver. You have multiple antenna at the transmitter and multiple antenna at the receiver. So the capacity has a new term which is like number of your bandwidth and SNR is there, but the new term is that your and it's a function of minimum of number of transmit and number of receive antenna. So this term is basically is new. So now if someone see that what is the another way to improve the capacity, simply you can increase the number of antenna, the capacity can be improved. Okay, so what is it really that simple? Like if you go and increase the number of antenna, your capacity is improving. Can we not go like why we can go and deploy 100 antenna or 1000 antenna? Is it really that simple? So the answer lies in the several limitations that we have. I will talk about them one by one. And so first, there was no requirement in early 2000 or those days. Why? Let's consider an example. Let's say some network provider selling you three kind of services. One service which provides a 10 Mbps of data rate at let's say 100 rupees per month. The second second service is like 1 Gbps of data rate at 500 rupees per month, and the third one is that 1 Tbps at 2000 rupees per month. So assume that you have like no like financial issue, which one you will consider buying? Even if you have no financial issue, most of the people will go with, I guess, option B, and some people who may, can opt for A also. Why people won't go for C, or why it is not advisable to go for C? That currently there is no single application in the market where you can utilize such high data rate. What you will do for 1 Tbps? 1 Tbps, there is no application. Even if you go for for all kind of normal routine work, even the plan A is fine, more than sufficient. There are some high-end applications where you may need plan B. So most of the people either settle for plan A or plan B. They won't think about plan C. So earlier days, like when we do not have that different kinds of applications, so there was no requirement. So there was no study as well. So since there was no requirement, people have not studied much about how your capacity behaves with number of transmit and receive antenna. Will the same equation which I talked about, whether it will still hold or it won't be a linear function, it may be a sublinear, or maybe after a certain antenna it will start decaying. We are not sure about that. Okay. Then there are several implementation challenges. What are those? So first is the size. So as I told you, the paths should be independent. So that constraint depends on the minimum separation between two antenna, and two paths to be independent in a MIMO communication. The antenna separation must be at least lambda by 2. So let's assume there is a 1 GHz operating frequency. So you can apply C equals to nu lambda, and you can find what is the value of lambda. So that will come around 33 centimeters. So the minimum separation would be around 16.5 centimeters. So you need at least 16.5 centimeter antenna spacing between two antennas. So even if you are deploying 8 antenna, your transceiver size would be around 1 meter. So 1 meter size is too huge for many devices. Like you cannot deploy, your mobile phone cannot be of 1 meter size. And even if you go for base stations, there also are certain kind of constraints. So deploying so many antennas was not practical. because of this constraint. Second, there are several challenges in the signal processing. Like since we are increasing the number of antennas, several fundamental problems which were addressed in the case of MIMO need to be reconsidered, like signal detection, how you will detect the signal, because your receiver is receiving so many signals in a multiplexed form. Then you have issues with the pre-coding, how channel estimation, pilot contaminations. So there are several fundamental issues that need to be addressed. And third and very important, cost. So every antenna needs to be supported by dedicated RF chain. What we mean by RF chain, it should be like having several capability, like all baseband to passband conversion, amplification, low pass, high pass filtering, all those processing will happen at the RF chain, and it will, the unit which will be connected from your baseband unit and towards the antenna. So RF chains are costly in terms of money and also in terms of power consumption. And if you have, because you need to support several, like you have low noise amplifier, you have other filters and other things, so that requires certain level of powers to operate. So that may lead to a poor energy efficiency. So these are the limitations, but thanks to all the contributions made by the research community across the globe, academic as well as non-academic, both. So what some of the efforts which are made, I am just highlighting, the requirement wise, it was first envisioned around 2008 that we need, because there are we are able to see there are some potential applications and that may require a very high data rate. So so that happened around 2008. Since there was a requirement, people started doing several kind of studies, and this was the first you can say formal study on massive MIMO, where it is done by Professor Margetta at Bell Labs, USA. So it is about non-cooperative cellular wireless with unlimited number of base antenna, and for this work, Professor Margetta has received Marconi Award in 2013, which is the highest award in the field of communication, and given by a communication society. And in 2015, he received IEEE Baker Award, which is the highest award in category of IEEE across all the fields, all the societies in the wireless communication. And he was the last recipient for IEEE Baker Award as well. So this was one of the most fundamental work in the sense of massive MIMO. Then there are several parallel works to realize or address the implementation challenges of massive MIMO. So huge size. So earlier days we are only limited to one-dimensional array. So all antenna will be placed in a one-dimensional in an array format. So the people have started carrying out research so that we can place antenna in a two-dimensional planar array, or in a plane, or in a three-dimensional object. So that has a new term like full dimension MIMO. So if someone interested, they can look into the full dimension MIMO. And also because we are exhausted with the current bandwidth, people have started with higher operating frequency. So higher operating frequency means you have shorter wavelengths. Shorter wavelengths means you have luxury to pack more number of antenna in a given size. So these two approaches complements or address the size limitation of the massive MIMO. Second, complexity in signal processing. There are a lot of work happened in the last decade about signal detection, pre-coding, channel estimation, and so there is one very good paper. I'm not going to cover all those details because it is already in a matured stage and people are using it also. This paper although it published in 2014, and after that also people have worked on this part. So this paper, an overview of massive MIMO benefits and challenges. So this paper covers all those problems which I have addressed about signal processing, and they have given some detail about that. So if someone interested, they can go and check this paper. And high cost, so the answer is that that we want to increase the number of antenna, but we want to maintain like with the number of RF chain. We don't want to increase RF chain by a huge factor. Maybe one or two RF chain, or maybe we can. That is fine, but we don't want like a number of antennas are 100 and RF chains are also 100. 10 RF chain, 100 antenna. We want something like that system. So we started looking into the aspect of beam forming and beam combining, and this work. This is one of my paper. It was published in 2017. It is about the beam combining. So beam forming, we typically use this word at the transmitter side, and beam combining we typically use at the receiver side. So this paper talks about the beam combining, and this is one of the very early paper in this topic. So if you are interested, you can explore this also. So I am just waiting for for 5 seconds. If you want, you can take a screenshot, or you can take a photo of this slide so that you can at least go through, you can have these references with you. Okay, so I am moving towards the so since we have addressed all the issues, or several issues in the massive MIMO, not all. So there are two realization of massive MIMO exist in the literature. The first realization was named as large MIMO. It is basically extension of point-to-point MIMO. What is the point-to-point MIMO? We have one transmitter, one receiver, and you have multiple antenna at the transmitter, multiple antenna at the receiver. So this is something like this form. But so you have very large number of antenna at the transmitter, and we have a very large number of antenna at the receiver. So from the base station perspective, it's okay, we can have large number of antenna, but still after even doing all this like different kinds of array or millimeter wave communication, still that user device cannot be very big. It should be compact. So since it's a point to point, we cannot deploy more number of antenna at the other side. So deploying more number of antenna, it's very difficult at this side. So what are the possibilities that we can have one small tower kind of thing at a rooftop, and all the devices inside that building is connected through that. So the application wise, it was very limited, and that's why it was not kicked off. Like people have started this work around 2008. Professor Chokalingam in ISC, he started this work, but this work was not kicked off, and later Professor Marjata, he proposed a multi-user realization of large MIMO. So what is that? So basically he assumes that there are multiple users, because user density was increasing, like there are more number of users in any cellular communication, and they all are trying to access the base station. They all trying to communicate with the base station. So in that case, any particular time slot, you will have sufficient number of users. They are located at this different locations. So this lambda by 2 constraints is automatically satisfied. So what base station will see? Base station will see, I am receiving a signal from different antennas located at different places, and those are all transmitting independent data stream. So this was more realistic, although there is no difference, literally no difference mathematically between these two models, large MIMO or massive MIMO. But in terms of implementation, this is more suited for cellular communication. And that's the reason this kind of realization is part of all the recent wireless standards, not only 5G, even if you go for Wi-Fi standard, Wi-Fi 6 and other wireless standards, nowadays almost, if you see, almost more than 30 or 40 products are available in the market which uses this kind of approach. So what is the role of massive MIMO in 5G? That's the another important question. Now we understand that how massive MIMO can enhance your capacity, it can improve, provides very high data rate and capacity. What is the role of massive MIMO in 5G? So let's first understand a brief about 5G. I won't cover 5G in very detail, very briefly. So 5G basically, unlike earlier generation of like 2G, 3G, 4G, 5G does not focus only on data rate. It classifies 3 use cases. First is enhanced mobile broadband, which talks about very high data rate. Second is ultra reliable and low latency communication. This is the same which Professor Lalit Avasthi was talking about, and that remotely a doctor can operate. So you need a very reliable kind of communication and which has very low latency. So if a doctor wants to make a cut from from a city to a remote place, so those things should happen at very immediately with very fine precision. So we need ultra reliable low latency communication, and then we have massive machine type communication, which we talk in the sense of IoT. So all these 3 use cases are the primary 3 use cases. So if you see this triangle, there are 3 vertex, and all 3 vertex are highlighted. Like the topmost vertex is the enhanced mobile broadband, the leftmost vertex is massive machine type communication, and the rightmost vertex is the ultra reliable low latency communication. Around these 3 vertex, all the applications are placed. So if you see your self-driving car, or your industry automation, or healthcare services, those all comes here, ultra reliable low latency communication. They are closed in this vertical. So if you see here, this is self-driving car, healthcare, all these things are closer towards this vertex. Similarly, smart city, where you have many IoT kind of devices, those are close to the massive machine type communications. And if you see the enhanced mobile broadband, there are 3D videos, USD screen, gigabytes in a second, where we need actually very high amount of data transmission. Those applications are towards enhanced mobile broadband side. So based on 3 use cases, we classify several key performance indicators, your peak data rate should be in EMBB case should be around, for downlink it should be around 20 Gbps, and uplink it should be around 10 Gbps. Similarly, we define it defines spectral efficiency, it should be around 30 bits per second, and for uplink it should be 15 bits per second. Similarly, if you see for URLLC, now you just focus on the latency part. These terms are not there in any earlier generation. So if you see the URLLC use case, there are user plane latency and control plane latency. So the latency is now for order of 1 millisecond. So that is expected. So any technology we are using for 5G, they must support this kind of ultra reliable, very low latency of order of 1 millisecond. Second, you can see the connection density. So connection density wise, it should be able to support 10⁶ devices, almost 1 billion devices per kilometer square. Similarly, there are issues with the reliability. It should be of order of 10⁻⁵ success probability if you are transmitting a 2-layer data unit protocol within a 1 millisecond. time period. So the reliability should be of very high order. So all these like different parameters have been defined, and any technology which should come into and for the 5G, they should able to support such kind of numbers. So let's focus on this. Just keep this in mind that peak spectral efficiency for massive MIMO is 30 bits per second and 15 bits per second. I will come to this later. Let's move towards. So since so how massive MIMO is playing role here? So massive MIMO, as we have seen that it is all about improving the data rate. So it definitely looks promising for improving, like for supporting all this EMBB application, which is enhanced mobile broadband, where you will have very high data rate. So how it has been implemented in massive MIMO, it is not in a conventional way where we have just think of improving it in terms of data rate. It has been implemented not unlike with the spatial multiplexing approach. It is implemented to help beamforming. Now, what is that? Let me explain you. So this is a typical 5G chain which is used for data communication. I have taken this picture from a website called ShareTechNode. So this is in this chain. What we have some code words. Code words are, you can think of like it's a all data bits. All data bits. It is we are doing some kind of scrambling, then modulation, layer mapping, and so layer mapping is the term which is used for spatial multiplexing in 5G specification. So if you go and read 5G specification, you won't find anywhere the term spatial multiplexing. You will find number of layers. So 5G allows a maximum number of layers, 8, which is same as 4G. So it looks like there is no increase in number of layers, at least whatever the current standards have been proposed. So there are two versions of 5G standards has been released, that is release 15 and release 16, and both release has considered only 8 number of parallel streams per layer, which is same as 4G. So there is no difference in terms of number of parallel data in 4G and 5G. So what is different? So the difference then is that beamforming. So what we do here, whatever data like comes out from after this layer mapping, it has been pre-coded with. So this pre-coded is, you can consider this a digital pre-coding, and after that all this OFDM signal generation happens, and then again there is an analog beamforming. So every data unit here is being transmitted through this whole process. We call it as a beamforming. So there are 2 levels of beamforming. There is a separate name for that. We call it a hybrid beamforming. So in this way, massive MIMO is implemented. So now you can see here there are multiple antenna at the front end, but actually all the antennas are not transmitting individual different data. It is basically transmitting maximum 8 number of data multiplexed in a certain way, and improves the overall, like in SNR at the receiver side. So let's first understand what is the beamforming. So beamforming basically, let's say we want to speak with someone. How we will speak? We will simply turn our face towards him and we will speak. So that's the conventional way, where you can rotate the antenna physically and improve your directivity gain. But there are smarter way. What are the smarter way? Via controlling the phase and amplitude. So here you can see one diagram where the signal is ST, and there is some W1, W2, and W8. These are the gain controllers, so which basically controls the amplitude of the signal. Then we have phase controller, theta1, theta2. So after this, you will receive some signal S1T, S2T. So mathematically, right? So this will be something like you are getting a signal which is sum of this S1 to S8, and which is mod of raised power minus j d theta. D is the minimum distance between these two elements, these two phase controller elements or antenna elements you can think of. Okay, so but it can generate a beam. If you adjust these values, it will generate a beam in a particular direction, but it will only generate a single beam. So with a single beam, you can support only a few sets of users which are in that line. You cannot support multiple users which are located at different places. So what should we do to generate multiple beams? The answer is that we need parallel structure like this. Like same signal is like generating one beam, and we need another parallel structure and that can generate another beam in for that. So this is a typical diagram. If you notice here, we have a digital precoding matrix at the leftmost side. So we are getting KT data streams. Okay, and it is going through the RF chain. So we have KT number. We only need KT number of RF chains, where you have a number of antenna. So all this data is these small elements, which is you can see with arrow marks. These are your basically phase controller. So it changes the phase of the signal, and we are adding this phase shifters with some some signal from. So every signal has a contribution at this antenna. So it's a composite kind of signal, which is all this KT signal is multiplexed here, and they are transmitted from this antenna, and this antenna. So this is. So here, this helps what it achieves. This helps in improving the SNR. It also achieves because we have a beam which is very narrow or very directed. So there won't be much interference. It will suppress the interference. Further, it will, because it has improved the SNR and avoid the interference, overall throughput experience will be enhanced. And then here notation wise I already explained, this is your KT is your data streams, NT is your number of transmit antenna, and NT is considered very high compared to your parallel data stream. So like in 5G, typical numbers are we have 8 data stream and 64 antennas. Okay, now the second very important question, we talked about number of antenna, we talked about this, but how big can a massive MIMO be? There is no theoretical limitation, but so far we have implement the biggest massive MIMO is with 128 antenna. So this was an experiment done at University of Bristol and University. In this you can see there are 4 racks. Each rack has, now you can see there are 32 antenna, like it's an 8x4 matrix. So we have 32 antenna in each rack, and we so that we have total 128 antenna. So the system parameters are 128. It has been operated at 3.5 gigahertz frequency. Bandwidth was 20 megahertz, and modulation was 256 quad. So the spectral efficiency achieved at this, using all these, was 79 bits per second if you consider 12 users, and if you consider 22 users, the spectral efficiency was 145 bits per second. So this is, it is not a commercialization, but it's a prototyping of the massive MIMO, and this is so far this is the highest number we have achieved, and it has been registered in Guinness Book also. So if you compare this number 79 145 with our expectation was, if you remember that I told that we will come back to spectral efficiency, that 30 bits per second for downlink and 15 bits per second for uplink. These two numbers are very high compared to what is the minimum we have set for 5G. To understand what 145 bits per second per hertz means, you simply multiply with a 20 megahertz system. So if you multiply with the 20 megahertz, this will be around 3 Gbps. So you will get that much amount of speed in this system. So we have seen it's like massive MIMO is only for eMBB use case. Like we have seen all high speed, high data rate, or whether what about the other two cases, that is URLLC and MMTC. Just to recall, 5G has 3 use cases. One was the enhanced mobile broadband. The other 2 cases were the ultra reliable low latency communication and massive machine type communication. So we will first talk about the URLLC case. So URLLC basically it is more about reliability. So link reliability is a function of channel variations. So higher the channel variation, lower the reliability. So massive MIMO, because it has so many antennas, it reduces the channel variations, and that thereby improves the reliability. Let's understand this by one example. So consider the received signal at a user. This is y equals to hx plus n. I have not specifically mentioned here what are the dimensions. Just I am commenting here. So y is like one. Let's say user has only one antenna, and it is receiving a signal from a base station. So that base station might have NT number of antenna. So this x is NT cross one vector. H is your that channel coefficients corresponding to each path. Y is just a single scalar quantity, and noise that has been added at the receiver side, that is also a scalar quantity. So and assume that we use a match filter approach. So what for decoding the signal, this signal. So what is a match filter approach? We simply multiply by the Hermitian of the channel matrix. So in this case, it is a vector. So it will be just multiplied by H Hermitian Y. So if you multiply this, what you will get? Basically, you will get H Hermitian H, which is norm of H square. H Hermitian H means basically you are multiplying a row vector with a column vector. So it is element to element multiplication and sum of all the elements. And then we have H Hermitian N. So assume that your channel is Rayleigh distributed with a mean 0 and covariance matrix, identity covariance matrix. So variations of this H reduces by NT. What do I mean by that? This norm of H square, if you find the what is the distribution, so 1 upon NT norm of H square has a mean 1 and variance 1 upon NT. So your variance is very low. So what we mean by variance is very low? So basically your value will be centered around the mean only. So you will be very confident that whatever you have received, that the value is this. And if you use this property, so your norm of H square x, the first term here approaches to NT times x, and the second term, which is basically using the same property because H and N are basically uncorrelated, and because of the high dimension, it will become nearly orthogonal. So this value will approach to 0. So that leads to an improved reliability. So it's your detection becomes very simple, and your reliability will also improve very high. So in that sense, massive MIMO definitely supports very high reliability, and so that makes it fit for URLC application as well. Now let's talk about the massive MIMO for MMTC. Whenever we talk about MMTC, it is more about low power. What we mean by low power, let's say you have a smart meter at your home. So no one physically comes to your home to check the reading. The meter itself will send a monthly basis or maybe weekly basis readings to the grid. So it requires very small amount of data communication. So it does not need very high data requirement, but yes, it needs a like a power like battery which should last for a long period. So we'll see how massive MIMO can support for this. So if you see due to beamforming techniques, whatever we have seen, massive MIMO provides an array gain in terms of SNR improvement. Now, since we have SNR improvement, this SNR can either be used in two ways. Either you extend the coverage, means since your SNR is better, you can cover more area, or you can reduce the transmit power because you do not need that much amount of power for transmission, because a lower SNR also you will be able to do in a good way. So that will lead to your low throughput, but at the same time your battery power will, like your device will have more longer battery life. So assume there is an SNR gain of 20 dB. So what we can do, we can reduce the transmit power, let's say by 10 dB. So what it will do, so we have reduced the transmit power, but we have 10 dB of SNR gain. So we will have higher data rate, and at the same time, since we have reducing the transmit power by 10 dB, it will increase the battery life almost by 10 times theoretically. So these makes massive MIMO fit for MMTC application as well. So we have seen that massive MIMO covers all kind of use cases. It is it primarily designed for eMBB, but it can support URLLC and MMTC both. But what is next? What, like if you see nowadays, there are so many products available in the market already. Several companies like Ericsson, Samsung, they have deployed massive MIMO in different part of the world, not in India, definitely. So what is the next? Like what is like why we cannot go for 256 antenna, 1000 antenna, 10,000 antenna? Can we do that, or what are the challenges in doing that? So we will see how massive MIMO potentially can evolve down the line in 10 years. So the next part of the presentation is basically taken from this paper, Massive MIMO is a reality, what is next? So if you are interested, you can go through this paper and read in more detail. So the first, we can see a very extremely large aperture array. What we mean by very large aperture array? So here I have shown two kinds of this applications. First, that this in the top of the building, you can see there are some antennas. So these are we call it as a co-located antenna. Co-located arrays. So it is possible that instead of mounting all the antenna in a single base station, there will be a very like co-located arrays of antenna. They are placed in the rooftop of a building oriented in a different directions. So that will give you a more area, and all of them are connected at a central node. So this may be one possibility. The other possibility is that the entire building we can use to transmit the array. So let's say this is a very big building, let's say 10 floor of building or 20 floor of building, let's say 20 floor of building, of every floor having 3 meters of height. So you can think of 60 meter of height of this building, and let's say one area is around 6 meter. So you'll have around 6 meter by 60 meters. So what we are doing, we are in the entire building, we are placing like antennas, and so it is like wall mounted. It is not a separate structure. In the building itself, we have placed so many antenna. Now this entire building is looks like it's transmitting the signal, and so basically we are using a very large area or aperture size to deploy the massive MIMO. So this could be one possibility in that direction. The future massive MIMO can be saved like, but still this will throw several different kind of challenges. The second possibility is that you will the user uh, the is just like your all antennas are distributed over a large geographical area. Let's say we are in a city, and in the city there is only one base station, and the antennas are not placed at the base station. Actually, it is placed across the city at different locations. So till now, what happens that a base station is surrounded by users, but in this cell-free massive MIMO, a user will be surrounded by antennas. So many antennas that are serving in from different direction, and so this concept, the name is cell-free massive MIMO, because there will be no cell boundary, at least for in a very large city. Definitely, if you are going from one city to another city, there will be some cell, but considering a very large city, there won't be any cellular kind of communication. It will be all distributed massive MIMO. The third and important possibility is that holographic massive MIMO. This is altogether a new technology, and it is not only about the communication group. It requires several kinds of support from the RF front end and the electromagnetic engineers who work in this area. So this is all about developing a new surface which is basically have uncountable infinite number of antenna into a limited surface area. So this is you can think of, there is basically no array element. It is not a 2D array or something like that. It is a surface, and it generates a plane of waves, and one can perceive like he or she is receiving a signal from a very large surface area, or which has basically infinite surface area. So this potentially test you can say in the limiting sense, it will test the capacity. So this requires definitely a new direction. The names are holographic RF system and holographic beamforming and large intelligent surface. So here we have shown two approach. One, the first figure, the top one, you can see that there is a RF signal generator. So that signal generator generates a signal, and then it goes to the surface. This surface generates that signal, and that goes to the receiver. Another example is that you have RF transmitter, but the surface is not attached with the transmitter. Basically, this is using the conventional ways to send the signal to this surface, and this surface basically it converts into in a desired beam. It will generate a desired beam and send it to the receiver. So these two are the ways the future massive MIMO can be looked like. And if you want to have more detail on the holographic massive MIMO, this is holographic beamforming for MIMO. This paper was in 2017, and this another paper, the potential of using large antenna using on intelligent surfaces. The intelligent reflective surfaces, IRS, is a new term which is used for this kind of systems. All these two are the very recent papers, early paper on this holographic massive MIMO. If you are interested, you can go and you can read these papers. Okay, so far we have covered massive MIMO with the perspective of architecture perspective, how the shape will look like, whether it's extremely large array or it is a cell-free massive MIMO, or it's instead of array it's a plane, that is holographic massive MIMO, and all of them poses different kind of challenges in terms of signal processing. So So I'm not going all those challenges. I will cover one like very interesting approach where the future massive MIMO can adopt with. Okay, so that is all about intelligent massive MIMO, where instead of using all your knowledge of signal processing and all of those knowledge, it will be complemented with machine learning or artificial intelligence kind of approach. So here, so machine learning is especially useful when it is very hard to characterize a system. So when it's very hard to characterize a mathematical model or something like that, machine learning is useful in doing that. So let's say if you're talking about massive MIMO or very like antenna with 1,000 antenna or to 10,000 antenna, or in such cases, acquisition of channel information may make massive MIMO intractable, because you need so many antenna. Like in case of self-free massive MIMO, you are surrounded by so many antenna, and there will be some antenna which is you cannot even see. So it's very hard to characterize what is the signal between those two antennas, how the signal model behaves. In those cases, and channel information is very important to doing any kind of whether you do signal detection, pre-coding, any signal processing. Channel informations are quite useful. Thus, since it's very hard to model, it is machine learning approaches might play a vital role for this. So here, if you notice, there are 5 different applications has been listed. The first one in the top, optimal array placement and configuration. So it is about you may have a massive MIMO, which is maybe located at the rooftop, but it is not static. So it may be mounted on a rail or something like that, so that it can move across the different parts of this rooftop, so that it can provide a better coverage or better directivity gain to a particular user. And that may require some kind of machine learning to know what is the your fingerprint of the user, where user is located, and other part. Second is that ML based channel estimation. I will talk this part in more detail in the upcoming slide. The third one is the configure meta surfaces. This you can notice here. This is the configure meta surfaces to reflect the user. So what happens? This user is it not in the line of sight of this rooftop antenna array? It is blocked by this house. So what an intelligent meta surface will do? This antenna will throw a beam to this meta surface, and this meta surface will direct that beam towards the user. So it is just acting like a mirror, but it's intelligent. It will not the base station can configure in this direction. It has to direct the signals. So that also requires some kind of, because it's very hard to know again where user is located, how the base station will know, and how the base station will tweak this meta surfaces to do certain kind of reflections in particular direction. So those may require machine learning can help in those direction. The fourth one is the predicting the trajectory. So what happens nowadays, whenever let's say there is a phenomena called handovers. So what happens whenever we move from one cell to another cell, one sector to another sector, your signal, you as a user, we feel seamless movement, but at the back end there are a lot of communication happens. So but machine learning can help us to mitigate the handovers. So now what happens, whenever a signal received by a user, it is basically there are some kind of signaling mechanism which leads to a handover, successful handover. So how a machine learning can help? So it can record your RF fingerprints, like at 10 o'clock where you mostly are. If you are going to this direction, where you will likely will go. Let's say people who are have very stable daily routine. For them, it's very easily to predict at what time and like when to initiate the handovers, and directly you will start receiving signal from the another base station or a particular base station or particular sector. So that is another application, and definitely the fifth one, it will help all kind of signal processing at the baseband level, whether it's a detection, whether it's a modeling of pre-coding metrics or anything. Those can be modeled using the artificial intelligence or machine learning kind of approaches. So people have already started working in this area. I will talk to you about more detail about the DNN-based channel estimation. So how a DNN-based channel estimation will look like. So there are two phases it will be done. In the first phase, this is a diagram where you can see there is a signal XK which is being transmitted to a wireless channel, and this wireless channel we are receiving the signal and we estimate the signal. So in the first phase there will be offline learning. So what it will do in the offline learning, we have we send a pilot symbols to generate an OFDM symbol. So a symbol which is known to receiver and transmitter and receiver both. So your input and output are known basically. So you know the output because you are transmitting the pilot symbols. Input is you use that pilot symbol, you generate an OFDM symbol and send it to the wireless signal, and that is your input to this DNN. So this OFDM symbol is transmitted over different channel conditions and received, and whatever the receive, the transmit and receive symbol is fed to this model as an input. So this is your input, and you will try to minimize the distance, or you can say basically difference, and you need to define a character like function which can be define the difference between this input layer and output layer, and you will start learning all the weights, all the parameters of this DNN, this deep neural network. Okay, once you have done your learning, once you acquire everything, like what is the weight and everything, then it's the application phase. In the application phase, you are transmitting the actual symbols, actual data symbols, and you receive some signal at the receiver. You, instead of going through all this chain, you won't go through this entire chain. So basically this entire chain will be bypassed, and you will directly feed it to the input layer and you will get the estimated signal. So that will reduce the burden of doing all kind of signal processing, and or maybe at like all the signal processing which are intractable. So with that, so I'm summarizing this talk. So key takeaways. So we have seen how machine MIMO, what is the motivation, why we have gone for machine MIMO, and what are the challenges and how we have overcome. Then we have seen what is the role of 5G. So it was primarily for EMBB via beamforming, and then we have seen the massive realization, that is 128 antenna system, where we are able to achieve 145 bits per second per hertz kind of spectral efficiency. And then we have also seen it is not only supports EMBB, but it can also support URLLC and MMTC with the virtue of channel hardening and array gain. Array gain is basically your SNR is very good, and channel hardening, that it follows certain kind of like your variance is very low, and it has an orthogonal structure with the noise. So then we have seen like it in the future, it might extend to a very ultra massive MIMO kind of structure, where either you will have very extremely large aperture size, or you will have cell-free massive MIMO, where your antennas are deployed at different location, or you have a holographic massive MIMO where you have we will come out with this array kind of approach, and we will come to a new kind of technique which is basically derived from holography, which is used in optical kind of communication. And then we have intelligent massive MIMO to address all kind of signal processing issue where it is hard to model any mathematical model, or your machine learning or artificial intelligence kind of techniques can help us to achieve all kind of signal processing in massive MIMO or ultra massive MIMO. So with that, I'm thanking you all. These are my personal details. If someone wants to reach me out, they can go to my website or LinkedIn, or they can email me as well. So thank you, everyone. So if you have any queries, any questions, you can ask. Yeah, thank you. Hello. Am I audible? Dr. Avasthi?
Yeah, hello. Yeah, thanks. I would like to say my heartiest thanks to Dr. Shah for presenting such a nice talk. And I am sure that the audience has benefited by this talk, and they will remain in the contact with Dr. Shah. And for any further query, if right now they don't have direct questions right now, they can email questions with Dr. I'll request to Dr. Shah, please, if
yes, sure.
answer. So with once again, I would like to say thanks to Dr. Shah for giving this valuable talk. And for participants, the information is for regarding next session is that it will be from 2:30. So I would like to request to all of the participants to please join the session before 2:30 sharp. So thank you, Dr. Shah.
Okay.
Thanks to all participants.
Thank you, everyone. Thank you for inviting me. Yeah, thank you.
Thank you, sir.
Yeah, okay.
Very good afternoon to everyone. Welcome all the delegates to the second session of the Day-1 of this course. For this session, we have with us Dr. Satish Avasthi. He is currently working at NIT Jalandhar and he did his PhD from IIT Kanpur. His research interest includes peer-to-peer networks, complex networks, convex optimizations, social networks, application of linear algebra and game theory networks. And the topic he will be covering during this session is challenges in peer-to-peer networks. So we welcome Dr. Satish Avasthi as the expert in this session. Over to you, sir. Thank you. Thank you, Dr. Sukhvinder. Dr. Sukhvinder, can you start recording of this? Okay, once again, thanks to Dr. Sukhvinder for inviting me for a talk, so let me share my screen with you. Yeah, my screen is visible to all audience.
Yes, sir, it is visible.
Yes, sir, it is visible. Yeah, thank you very much. So, once again, thanks to the organizing committee for giving me this opportunity to deliver my talk. The topic of my discussion, my talk is challenges in peer-to-peer networks and few solutions which we would like to propose here, including my own. So here, it will be the outline of my presentation. So we will start first a brief history of internet and peer-to-peer network, then a brief introduction of peer-to-peer network, then the challenges which P2P network have, and possible solutions of these problems, and these solutions and algorithms which I will be covering few, and largely I will cover the absolute trust algorithm which is given by us. So, and finally the conclusion and few open issues which other researchers can explore and they can give the solutions for it. So this is all about the outline of our presentation, but references I will share in the footnote of wherever it will be used, so it will not be there in the last of the presentation. So you can note down the references, whatever, if you need it for your future reference. So let us start with a brief history of internet and peer-to-peer network. So Leonard Coinrock of Massachusetts Institute of Technology, he recognized the problem with circuit switching network and with the BRST data and he proposed that time sharing based communication system and the concept of packet switching system. He worked with Shannon, which is known to be the father of modern information theory, and there he inspired that how we can get the solution for the BRST circuit switching network. Then he published the first paper on packet switching theory in July 1961. It was the first paper which was in the packet switching network. And the first book on the same topic is published in 1964 by Coinrock itself. In parallel, there were two more researchers. They were also contributing for the toward implementation of circuit switching network, packet switching network, and they were Paul Barron of R&D Corporation around 1962 from UK, and Donald Davis of National Physical Laboratory of UK around 1965. But largely, their work is more or less focused on the engineering and architectural design of circuit switching network, of packet switching network. But mathematical theory and mathematical simulation, whichever is given, that is given by the Coinrock. So then there was in parallel, it was the era when there was the Cold War between USSR, which is nowadays Russia, and between the United States. And there was the the race to show their hold on the space. So, the space race was largely, So then, at that time, US has a lot of fund to invest on the project, which can make a one network. So this was ARPANET, Advanced Project Research Agency, which was funded by the Department of Defense US, was the one of the earliest, packet switching network. So this was, and around when it was initially, it was only 4 and 5 nodes were connected to each other, and earlier, the nature of this ARPANET was itself like a P2P network. So in 1969, the first host-to-host message was sent from Coinrock's office at University of California to Stanford Research Institute, SR. So his office his node was selected as the first node because he gave the first, theory for the packet switching. Therefore, his node was connected with the first node. So all the history you can see, it is available in Coinrock himself was sharing this in this IEEE Communication magazine, the article and early history of internet. You can readers can go through this this reference. It will be available on internet. On IEEE Explorer. Now coming to the then brief history of P2P network. So P2P network, what happened in initial days, it was used only by some corporates or sub-cooperative researchers in the universities to share the information like research articles, like book or notes. So from one node to another node, it was very limitedly used between the researchers, or by some companies to run the simulation work on many computers and worldwide, so that they can save their processing powers. So after that, in May 1999, one school dropout student, Fanning, of Northern University in Massachusetts, he introduced a popular P2P network named as Napster. So, and it gains popularity. It gained popularity in a very 1 or 2 years of duration, and it was largely used for the exchanging of music files. But then there was the issue between music companies and the owner of Napster, and after a long legal fight, Napster was forced to be shut down. So that was the birth of next generation, peer-to-peer network, which when there was purely distributed network. Napster was somehow some nodes were there, so which were called the organizer of the node. I think some noise is coming from there. Dr. Pawan, could you, yeah. Okay. So, and up to June 2016, BitTorrent is one of the popular, P2P network. Accounts around 5% of the total daily traffic in North America and Latin America. So this is how the journey of P2P network was traveled from its, initial days to here. Let me give a brief introduction about the P2P network. What is P2P network? So it is a decentralized communication model in which each party has the same capability of being server as well as client. So either party can initiate a communication system, and any data or file can be transferred directly between peer-to-peer in a peer-to-peer manner. On the other hand, the client-server model, in this model, client makes some service request and server fulfills it. So this is the main difference. So in one line, what we can say that P2P network model allows each node to act as a client as well as a server. So this is the main difference between peer-to-peer network and client-server model network. So its survey is available in this, which is an IEEE communication survey tutorial. You can go through this. Now, P2P network, why we are going for the P2P network? So there are a lot of advantages over the P2P network over client-server model. First of all, because a lot of nodes are connected there, so the diversity of data which is available with the different nodes, it can be used by many other users. Its robustness against single point failure. Even if some nodes are not, maybe because of failure of the power or processing thing or anything, or damage because of anything, so our whole system will not damage. Because unlike in the client server, if suppose server is down, so your whole network will be down. But in P2P network, even if few nodes are not working or they are not contributing anything, so our whole other nodes can contribute and our network will run. So single point failure kind of question is not there in a P2P network. It is scalable in the sense that as a new node is joining the system, so it is coming with its own infrastructure also. So it is scalable as far as we are increasing the nodes, we are getting more and more processing power and storage and all everything. We can only 3-4 nodes can start to make their own network. So it needs only a very small initial setup cost. So and low maintenance cost is also needed. Is needed because we need not to maintain the costly server, so a very low maintenance cost is required there. Now let us give you a brief introduction about the challenges which P2P network is facing. Fundamentally, because there is no control on the user, so there are two challenges which I would like to highlight here. First one, because the node, which is where the person who is sitting on any particular system, you don't know how it gives the opportunity as well as the challenges that it can give an authentic file or the virus which can corrupt your whole system. So that is the malicious peers which can destroy the system, whole system. Is one of the issues which P2P network can face, because everybody has a right. He can be the server, and it may serve the virus to the other system. Another one is that P2P network, because the motivation of P2P network is that everybody should contribute to the network. But if suppose some free riders are there, they are only taking the resources from the network, they will only become the burden on the system, and in this way, P2P network will its purpose will be defeated, because in overall what we will get, it will work like a very poor client and server model, where the bandwidth of the server itself will be very poor. So let us see the few experimental studies which was done by many researchers, and it is observed that first study was conducted on Nutella network, which is the second generation P2P network by Ada et al. In 2000, and which shows the following observation. The observation was that 70% users did not share any file, and 70% of the files are shared by 5% of the peers. Third observation was that top 1% peers shared 37%, and top 20% shared only 98% of the files. Second experimental study is conducted by Sarayu in 2002, and they observed that 25% of the users in Nutella did not share any file. 75% of the users in Nutella shared only 100 or less number of files, and 7% of the peers shared majority of the files. And 40 to 60% users shared 5 to 20% of the total files in Napster. This studies was done in 2002. Recently, in BitTorrent. The study was conducted by the researcher in 2013, and they concluded that 3% of the publishers are responsible for 67% of the contents and 75% of the downloads. And anti-piracy agencies or malicious users are responsible for 30% of the contents and 25% of the download sessions. So these were the few studies, experimental studies, which was conducted on by various researchers in time to time. So it focuses in the challenges toward the popularity of P2P network that we need. Largely, these two can be categorized into two categories. First one is the presence of free rider, and second one is the presence of malicious peers. So, these possible solutions, which is now researchers are looking toward to handle these two things, are to implement the trust and reputation system and to motivate the peers to share something or to do something, some incentive mechanism in the whole network, so that everybody is motivated to share something in a network. So these two actually solutions are not only restricted to the P2P network. Even you know that nowadays the e-commerce market rating systems, it is nothing but a kind of reputation system in which we are using, users are giving the ratings to the product, and product is being is establishing its own reputation in the market, and based on that, new user is thinking that whether I should buy it or not. So the reputation, trust and reputation system is this solution is can be implemented in many other fields also, not only in the peer-to-peer network, wherever there is and human beings are involved. In fact, it was said by Professor Pollack of Yale University that the new, after the invention of game theory or the introduction of game theory, new Nobel Prize will definitely go once in the field of reputation, because it is deciding. I mean, it decides always that how some people are dominating in the system, and how the rumors and all things are created in the society. So these two are the possible solutions. Let me introduce you that how these two solutions can be used, or what are the algorithms which was given by many researchers in the past, and what were their limitations, and what new things can be done in implementation of these two things, and particularly looking after the aspect of peer-to-peer networks. But it can be implemented in any distributed system. So what is the trust and incentive mechanism? In fact, I'll discuss only one part, that is trust and reputation system, and because of the lacking of the time. So before introducing the trust and reputation system, let us introduce two definitions. The first one is a numerical value which models the past behavior of peer or any person in the network is defined as a trust. So it is some mathematical function in which we are capturing the behavior of any person and predicting that what he is going to do in coming future. Second one, the value of trust evaluated by any peer based on direct interaction it has had with evaluated peer is defined as a local trust. So because any peer cannot, you have never interacted directly with Barack Obama, we have never interacted directly, or hardly the people has interacted with the any person, but somebody has interacted them, but they have some reputation in the whole society. So whole reputation is built based on some local interaction. So how that reputation is building? So that the primary or the raw data which is there for all those things, which is called, this is called the local trust. Third one, which we are calling as a reputation, it is the value of trust system as a whole keeps on any peer or any person. It is defined as a global trust. So globally, I mean, how globally somebody is being trusted, we call that. It is, of course, how we are building it. It depends purely on the raw data, which we are calling as a local trust. So these are few popular algorithms which were used in trust and reputation system. Eigentrust algorithm power trust algorithm, flow-based reputation, global contribution approach, and lastly, absolute trust algorithm. This was, so let us discuss these one by one, and its mathematical aspect we will see. So this is one of the fundamental work which is done by Kamrav of Stanford University, and his base paper, which is assumed to be the fundamental paper, and it is inspired by the Google's PageRank algorithm. That the notion of, let us go back one slide back. So from definition 3 to definition 4, how we are going there? What we are taking input as a local trust value, and based on that local trust value, what we are doing, we are evaluating the global trust of any person. So whole things what we will do, we will see in each algorithm, we are trying to build a global trust from given input of the local trust. So the basic notion which Kamrav used and his team used, that if I have some trust value on a friend and my friend is saying something about my friend, so I believe more on the person whom I believe. Correct? If suppose I believe on person A and person A is saying something about person B, so whether I will trust on person B, it depends on how much I trust on the person A. So it is based on the notion of friends of friend. It can also be, but can be interpreted as a weighted average of the local trust. This weighted average part will be more clear when I will discuss the absolute trust algorithm part. So in this, and weight factor is used, global trust is used as a weight factor of any particular person. So then there was a notion of pre-trusted peer. That means there will be some initial user of the network, those who made the network. They will be trusted by all the users, and some factor will be given to it, which we call by a factor A, and the global trust is defined T by equation number 1, that is 1 minus A T norm, where T is the trust matrix, correct, where it is T norm is a normalized trust matrix, and its element represent the local trust of peer J evaluated by peer I. So this is the mathematical equation which is given by the Kamrav. It is, and by using the power method, and by which directly the Google PageRank is using to its left principal eigenvector. So it is being calculated by using the same power method, and global trust is calculated using this equation number 1. So this is one of the fundamental work which is proposed in 2003 by Kamrav and his team at Stanford University. Kamrav is now the professor at MIT, and he is still working in the same field. So then the next work in parallel to this eigentrust algorithm, which is given by this Zhao and Wang, University of California, if I am not wrong. Yeah. University of California, correct. University of California. So, and it is a basic idea what they have taken. It is almost like the eigentrust taken from eigentrust algorithm. And the modification was that the higher reputed peers, those who are in the node, they are selected as a pre-trusted peer. Instead of some initial design of the network, what they said, that if suppose some people have designed the network, but now some other people has earned some more reputation in the system, then they will be treated as a pre-trusted peer, and all the rest of the people network can trust on them, and the reputation of all of them can be designed by this. So by this, what they have decided. And another thing which they suggested, that power nodes are searched and elected dynamically in the whole network, and then they can be chosen as a powerful node. Second thing what they use, that the speed of aggregation or the speed of convergence of this global trust was very fast because enhanced trust matrix, which is a square of trust matrix, was used. And as you know, that whenever we will use the square of trust matrix, it will always, its left principal eigenvector will always be easier to find out because the speed of convergence will be just double to that of the eigentrust. So this is the slight modification, but largely it is also based on the Google's PageRank algorithm, and it is the concept or the notion which is used here was also the friend of friend. But still they also used the normalized local trust matrix, which was the primary issue. Then flow-based reputation, which is given by the Shamon and Bill, and they identified the problem in ranking mechanism. And what they have done, the trust matrix without normalization they have used for the purpose of aggregation of local trust. They gave the local trust value in the range of 0 to 1, and it is also based on the notion of again the weighted average. And in this case also the left principal eigenvector of the trust matrix was also used as a global trust. So a very small modification was there, but again in this case also the global trust vector was calculated using the power trust method. But the major limitation of this flow-based reputation was that it cannot be implemented in a distributed system. So that means we have dependency on some central server, which is again, failing, our fundamental purpose of peer-to-peer network, which that means each peer, there is no need of any central server. If we will depend on central server, the purpose of peer-to-peer network will be defeated. Then Nishida, a tell from Japan, what they have proposed, the global contribution approach. They proposed this approach for to overcome the free riding approach of peers in the network, and they calculated the global contribution index in whole network by using equation number 3. This is again one contribution in which contribution depends on the contribution of other people from where we are downloading or from where we are uploading to the system. So these are some equations, linear equations, and in which these linear equations are made diagonally dominant, and they can be calculated using well-known Gauss elimination method, which is very popular methods available in the linear algebra. So this is the new approach which was used in global contribution approach. Then recently we proposed absolute trust algorithm, and we had few motivation for using these after doing a lot of what we have done. After going through the work which was done in the past, starting from the Kamwar's work from Stanford University to the Wang's work from the University of California and Nisda's work, we have seen that there are few limitations, few problems in ranking algorithms. Correct? Although PageRank is the most successful example of reputation system which is used by the Google engine, but in which reputation is decided by its popularity on the web page, and the popularity is measured by two factors. Number one, the number of links that point to the page, and second one, from where the link originates. So based on the similar concept, reputation system was proposed by peer ranking in all previous systems which we have already explained to you, but in which the most trustworthy peer is considered as the most reputed one. One who is trustworthy is considered as a reputed one. Correct? So the examples which we have discussed already. So the recent work which we proposed in this absolute trust algorithm, the basic motivation is first one is that ranking itself is not adequate to decide the trustworthiness of a peer. Because ranking will only tell that among any two peers that which one is the better. We will never know that whether they are trustworthy or not. We have to make a mark, a boundary line that beyond which we should say that yes, these are trustworthy and these are not trustworthy. Suppose any peer has sent a query and all malicious peers has replied. So using the ranking peer, what we will know, we will only able to decide that which one is better among those bad, malicious peers. We will never be able to identify whether they are, malicious peers or they are good peers. We will never be able to identify. A ranking system can only do what they can do. They can only rank them. Yes, this is first, this is second, and this is third, which is fine for the page ranking system. But when we are trusting somebody on downloading the file, we need to, identify their complete history, whether they are trustworthy or they are not trustworthy. Correct? Secondly, there is a difference between popularity and trustworthy. In many YouTube video, that many videos are there, they are getting many dislikes. They are not liked by many people, but they are coming on the top of search because they are being visited by many, users. So they are popular, but they may not be trustworthy. So these two are two different phenomena which we need to take care which is different from the page rank, which is making it different from the page rank. Thirdly, the most reputable peer are always overloaded. Suppose in the system, the ranking system is giving what the rank 1 for the top peer, and every request, if some new user is searching for some content, he will always send the query to the top reputed peer, and he will always be overloaded, and by that way, that reputed peer by default has to be reject the request from different peers, which is not a good situation in a peer-to-peer network, particularly when there are some trustworthy peers are already available in the system. Lastly, updating the value of normalized local trust to other peer is a message consuming task, which needs a lot of overhead in the system and which ultimately degrades the quality of service if it is being calculated in the distributed network. So you can go through this reference which is available on the internet on the IEEE website. It will be available there. So let me give you the brief introduction about this absolute trust algorithm in more detail, because at least it will give you the primary thing that how it is calculated, the global risk is being calculated. So the basic philosophy which we use in absolute algorithm, trust algorithm, is that local trust is always weighted average of these three things. Let's suppose any peer is giving ng number of good files and n number of some average files and nb number of bad files. So to peer I to peer j. So its trust on Pij can be calculated by the weighted average of these things. I mean, higher weight will be given to the good file, lower weight will be given to the lower file, and average normal weight will be given to the neutral file. Typically we can choose ng as a 10, nb as a 1, and nn as a 5.5. Therefore, nt, which is the summation of these, wg can be wg can be 10, wn can be 5.5, and wb can be 1. And based on these numbers, we can find out the local trust of Tij. So this is a very simple simplification. After substituting this wj in equation number 4, we will get this equation number 6, which will give us this total Tij in the terms of a fraction of satisfactory file and fraction of unsatisfactory file. So this Tij trust on local trust can be calculated in this way. So in any evaluation process, second thing is that in any evaluation process, there are two parties. One who is evaluating, we will call it the evaluator, and one who is being evaluated, we will call it the evaluatee. Reliability, the reliability of any evaluation depends on the person who is going to evaluate you or going to evaluate. Evaluation is said to be more reliable if it is being done by some competent evaluator. These are some few notions which we use in our daily life. Of course, if some competent person is evaluating somebody, we say that this evaluation is more trustworthy. We should trust on that particular thing. So here are three scenarios in which one to many, that means one person is evaluating many persons, many to one, where many persons are evaluating one person, and one to one, that means different persons are evaluating different persons, like this. these three could be the scenario in our daily life. So in one-to-one scenario, the basis of evaluation can be considered to be uniform because one person is evaluating all other persons. So we are saying that if one person is giving, like in a class teacher, if teacher is giving marks to all students, so in one section we can say that if one person is evaluated by many persons in a particular subject, so what we can say that the ranking of these students are uniform, correct, in that particular subject. In many-to-one evaluation, there are chances of contradiction. That means if one person is being evaluated by 10 teachers or 5 teachers in the class, one teacher is saying that yes, he is a good, another one is saying that he is not a good. So there could be a chance of contradiction. Then what to be said about that person? That is the question. The best way to resolve the contradiction is to take the weighted average of the evaluator's opinion while assigning more weight to a more competent evaluator. This is the basic philosophy which is being used in absolute trust algorithm. Lastly, in one-to-one evaluation, the evaluator and the evaluatee both are different, correct? And if both are different, then what is the way to make them uniform? Equation number 7 can give us the idea where we can do the evaluation input. If any evaluative value can be given as an input, and some weight factor can be assigned to that particular evaluation, and then it's P plus Qth root can be calculated as an evaluation uniform output. So equation number 7 can evaluate the evaluation uniform output. In this equation, if you will put Q is equal to alpha P, then 7 equation will become like 8. So the local trust is an example of one-to-many evaluation because one person is being evaluated by person, those who are around him. So it is the example of one-to-many evaluation. So it can be calculated using equation number 6, which is like here. So each peer is also providing the service to many other peers and is being evaluated by them. Therefore, it is an example of many-to-one evaluation, and the aggregate trust value in the system can be given by equation number 9. That means what we are doing, we are taking the evaluation done by each peer, local evaluation, and the global reputation or the global trust of that particular peer divided by its, which is weighted by this, and therefore we are taking this in the denominator. So this is the many-to-one evaluation. Now in whole network, every peer is evaluated by a different set. If the set can be represented equivalently as a single peer, then it is seen as one-to-one evaluation. Let us consider a set Si of m peers with global trust value T1, T2, and Tn. Then by using same notion of equation number 9, global trust of set Si can be defined intuitively like this. Here what we are doing, we are ensuring that the global trust of any set will be dominated by most trustworthy peer or more trustworthy by whole system. So this TSI is given by summation of Sij Tj squared divided by summation of Tj squared, equation number 10. Lastly, the global trust Ti of peer I can be biased by global trust Tsi of trust assigning peer Si according to equation number 7, which is the example of one-to-one, this equation number 7, which is one-to-one evaluation, where evaluator and evaluatee both are different. So the global trust Ti of peer I can be biased by the global trust Tsi of trust assigning peer Si according to equation number 7. If we will modify this thing Ti and Tpi there in the past, we will get the equation of global trust as equation number 10 after very small modification or manipulation in this equation number 11. We will get like this, where C is adjacency matrix corresponding to the T transpose, right? D diagonal T is a diagonal matrix, and in fact MATLAB also accept this function as a diagonal of T. EI is a row vector having ith element as a 1 and all unity vector ith element is a 1 and all the elements are a 0. Alpha is a constant which we have taken previously. T alpha in terms of P and Q, which we have defined here. alpha is equal to Q divided by P. So this is, now lastly, what we have got this kind of formula where D is this matrix, T is this matrix, and T is this 1 upon alpha. Now see, it is, now here it is a challenge to solve these set of n equations. Earlier, which power trust or eigentrust, what they have used a simple linear algebra, what they have used, if this board is available to you, they have solved a kind of equation T is equal to MT. This is a set of linear equations in which the sole purpose was to find out the eigenvector of this T of this non-negative matrix, which is very simple problem, and available solution are there in linear algebra, and popular solution is our method of solving this left principal eigenvector T. But our problem is different from this. What is there in our problem? Here, new function D, which is a function of itself T, and this is a non-linear function. So what it is, our problem is a kind of problem where T is equal to D, which is not a constant matrix, it's a function of T itself. You see the difference. A function of matrix D and a matrix M, T, and whole to the power 1 upon 1 plus alpha. So this was the challenge, that whether the solution for these and set of an equation exists. If it exists, can it be implemented in a distributed system? Can we implement this in a peer-to-peer network? These questions which we addressed in this paper, which you can go through. For more detail, it is written there. In a short, I would like to explain few theorems and algorithms which were used to solve these set of n equations. So, and it can be implemented in a distributed system because it is solved by iterative method, which was used like a power method was used to find out the left principal eigenvector of non-negative matrix. So now our question, forget about whatever we have discussed previously. Now everything we have captured in the form of mathematics. Now our question is to solve this equation number 11. Can we solve this equation number 11? Is the solution exist or not? If it exists, can it be implemented in a distributed system? Fortunately, we were lucky that we have got the solution for these, and it can be implemented in a distributed system. So let us have a few definitions before we introduce the primary lemma, which I will be focused on this thing, that how we can solve this equation, which is the fundamental contribution in linear algebra also, that how it can be, how we can solve these equations. So these the solution of these equations cannot be restricted only for this particular problem. It can be implemented in a various other fields, and it is open for the researchers, and you can use these things, its application in many other fields wherever it is required for you. So the few definition: a vector V or matrix M is said to be positive or non-negative if its each element Vi or M ij is positive or non-negative and real. Vector V dash and vector M dash is said to be less than V double dash and M double dash if its each element Vi dash and Mij dash is less than Vi double dash and Mij double dash. Lastly, the power of any vector V is defined as V to the power gamma, where ith element of vector V gamma is defined as like this. So power means if suppose any vector T, I am saying it is 1 by 1 to 1. So how we have defined that it is its power, suppose T to the power, we are saying T to the power 2. So we have defined there these like the power of individual element, that means 1 square is 1, 2 square is 4, and 1 square means this. This is a new definition which we introduced. Of course, it can be calculated, T can be calculated as diagonal of T as a matrix and multiplied by T. because diagonal of t is nothing but it will be 1, 4, 1 when you will multiply this by 1 to 1, 1 to 1, and when it will be multiplied by 1 to 1, so we will get the same result which is I have written here. That means 1 will be multiplied by 1, and you will get 1, 4, 1. So t square is nothing but diagonal of t into t, like this kind of expression. So this is the third definition which we have used. Now, we will consider there are many lemmas which we have proposed for the solution. First thing is that let z be a positive vector in Rz such that z is equal to ft with its ith element as this. Then there exists at least one pair of positive vector t dash and t double dash such that if t double dash is greater than t dash, then ft dash is equal to ft double dash. So here it is an n-dimensional analysis. I would like to explain you here the the simple part of it, which in 2 dimensions. What we are saying that if suppose in 2 dimensions, suppose here is a line and here is a t. For any continuous curve, if here is a one point P1 and another point is P2, correct? So what we are saying is, if it is continuous, so going from P1 to P2, certainly it has at least one root. It will at least intersect this axis at least once. It may move like this, so it will intersect this axis 3 times, but at least moving from P1 to P2, it has at least one solution. That is what is being said here in n-dimensional case, that it will at least one pair of vector t such that it is satisfying this condition. So it is framed like this. Second lemma is, this is very, very important lemma, which is the fundamental work and rest of the part which is based on this thing. So interestingly, what this lemma is saying, let A and B are n cross n non-negative irreducible matrices with non-negative acyclic, one point should also be there, non-negative acyclic and irreducible matrices with spectral radius 1 and corresponding eigenvector V. Then for any vector x having at least one component along vector V, this is correct. So in nutshell, what we are saying that if vector M, it has two matrices are there, M1 and M2, correct? So if it has a vector, V2 dot Vn eigenvector, and it has also V and U2, and only first vector is same, which is the highest one. So in this case, it is when this vector x will be passed through the multiplication of any of these two in any order, ultimately it will lead to the same vector V, which is a common eigenvector between A and B. This is a very fundamental theorem, lemma, which is the very best result, which is the fundamental result will be used in the next part of. Then this is extension of this lemma 8 is the theorem 9, that A and B are n cross n non-negative irreducible matrices with spectral radius of 1 and corresponding eigenvector V. Then for any positive vector x in Rn, A minus B to the power k dot x will be 0. This is another direct implication of lemma 8. Extension of theorem 9 is theorem 10, which is A1, A1, A2 and Am be n cross n non-negative irreducible matrices with a spectral radius of 1, lambda 1, lambda 2 and lambda n respectively. If the corresponding eigenvector for all the above matrices will be, then for any vector x, this is true, that is A1 plus A2 plus Am minus A to the power k into x is equal to 0 if it is satisfying this condition. So theorem 10th is actually the direct implication of the result which will be used to prove our theorem, which is theorem 12. The theorem 10th says that it exists, solution exists. Theorem 12 says that the vector t in theorem 11, which is there, is unique and can be calculated by an iterative function. The iterative function is given by this, where tk is the value of vector t in kth iteration and phi is the iterative function from Rn to Rn. So this iterative function is actually a useful function, and it is used to find out the left principal eigenvector of this whole system. And because it is being evaluated by iterative function, therefore it can be implemented in a distributed system. Thus, it can be implemented in a peer-to-peer network. That is the beauty of this iterative function. So its detailed proof is available in which we have given in the backup slides, which I would not like to discuss here. But in this theorem, what we will use the theorem 10 to prove theorem 12. So this is the main result of this absolute trust algorithm. So since algorithm 1 I am leaving here, this is how we are implementing this in a distributed system. Here we are using one trust manager peer, which will be the score manager peer, which will collect all score of any peer and which can be traced in a distributed system by hashing table, which is already available there in a structured system. So it can be done by using this algorithm, and only when the threshold trust value is more than some threshold value, then only we will allow to download to work as a source for any file or any resource. Otherwise, it will not be, and it can be calculated by this equation. This is the same equation which we have derived there in equation number 11. So this is the detailed algorithm which can be used in distributed systems, and its results I'm not going to show here because it will take a lot of time. A lot of results which is available there. It is available in my paper which I have shown there in earlier. Lastly, the conclusion of this work is that in this case what we are doing, aggregation is done without normalization, and hence it is true reflection of the past behavior of the peer. The calculation of global trust is done by iterative method, and it converges at some unique value, and thus it can be implemented in a distributed system. A lesser number of meshes are required to update the global trust. The algorithm can be implemented in a distributed system where no central authority is present. So this algorithm is robust against various attacks like individual malicious, unpredictable, and malicious collective peers, and it can be implemented. The load on good peers is more uniform as compared to the relative ranking mechanism. These things which we have achieved here. Now, open issues are there that this, whatever we have discussed, we have talked all about, only for distributed system. Structured peer-to-peer network, where hashing table is available and this algorithm can be implemented. Well, if there is a unstructured network where information is spread just by the never and never to never, in that case, this how it can be implemented, this formula can be implemented. This could be the open issue which other researchers can look into, and they can find out the solution for it. Another one is that one paper was there published on eigen trust value, that how what are those peers which are controlling the reputation of all other peers, and what is the minimum number of peers, correct? That if they will they will join together, that what is the limit on those minimum number of peers, such that if they will collide with each other, then they can control the reputation of whole society. That is what is being done nowadays in a society, that only few people are controlling the rest of the world. So that in the P2P network, let us find out the limit, that what is that particular limit, that how many number of people that they can control, or they are able to control the system, and what is the solution for that. And that this is another challenging part which can be done, is still open. Lastly, some available network like LinkedIn or Facebook or like that, where it can also be used, that if some user is posting some article or something which is not authentic, in that case how it can be implemented, this is another issue where it can be used. And for many only for the cloud, where in cloud computing itself, it can be used that where if tenant is which kind is giving their resources for rent, then the reputation has to be calculated how it can be implemented there. This is another challenging issue. Then another challenging issue comes that when in a crowdsourcing, nowadays we are collecting data using crowdsourcing, but many users, they used to give the fake data, and how to rely on that particular data. So using this algorithm, how it can be implemented there in a data source. This could be another open issue which researchers can look into. So this is all about the open issues and one or two algorithms which we have discussed. You can go through it. These papers, you can take its, you can take its snapshot, or you can read this paper. It is available in the IEEE website. You can also read the fundamental paper, which is given by PageRank Citation Ranking technical report by Stanford University Digital Library Technology. It is available there, which is the fundamental project. And parallelly, you can read these two papers, Power Trust Algorithm and Eigentrust Algorithm. So before understanding the complete work, my work, you need to go to these two fundamental work, like Zhao Wang's paper and Kaumar's paper. Then you will be able to understand how my work is. So this is all about the brief introduction of trust and reputation system and how it can be implemented in a system. I gave a very brief introduction and some open issues, open challenges which you can look into. So if this is all about from my side, if you have any questions, audience are requested to ask the questions. I'll feel happy. Here are a few backup slides which I would like to discuss. But if somebody is more interested to know the solution of these equations, they can email me. My email ID is available on my institute website also, or you can take it. I'm going to post it here. So with this, thank you very much from my side. I enjoyed this presentation and I would like to take the questions from audience. Thank you very much. Any questions, please?
Thank you so much, sir. If anyone has questions, they can ask Dr. Awasthi.
Participants, do you have any questions?
Well, if there is no question, then you can ask these questions to me later on. My email ID I am writing here. My mail ID again. Please feel free to post me the questions. I'll be happy to answer those if I can.
Sir, I have a slight doubt about the term peer-to-peer network.
Please.
Is it so that, for example, in case of WSNs, means wireless sensor networks, if the communication is possible between two sensors or among the different sensors, then can it be called the peer-to-peer communication?
Yeah, typically it is fulfilling the definition of peer-to-peer network. Whenever there is a communication between two peers without any, requirement of any central server, we call it a peer-to-peer.
Okay. So you mean that all the ad hoc networks, they will fall under the category peer-to-peer networks?
Yeah, whenever we are not depending on central server, we call it. In fact, the first generation peer-to-peer network, Nester, there was some dependency on central server, but second generation P2P network and now there's hardly dependency on central server except for registering somebody.
So does it also mean that the PCF mode in IEEE 802.11 will not be applicable to P2P networks? Only DCF mode of communication is applicable? Are you saying so?
Yeah, that I need to check the protocol once again, what you are talking about. But if there is a dependency on central server, it is loosely we can then. But even if we are transferring the file from peer to peer, we can call it peer to peer.
Okay.
We can call it peer to peer, but loosely it fits for the definition of P2P.
Okay, sir. Thank you.
Thank you, Dr. Pawan. If there's any questions from audience, audience can ask me the questions, please. Otherwise, I have already emailed my mail ID here. You can post your questions later on if it is not coming directly in your mind. Of course, for going through the complete work, you need to go through the papers which I was showing there. Then I think a few questions may come there. So that is what is from my side. Well, so
Thank you. Thank you, sir. Thanks for your time.
Thank you very much. Yeah, over to Dr. Sukhvinder.
Thank you so much, sir. And I believe the delegates were informed about peer-to-peer networks through your talk. Regarding tomorrow's time schedule, I believe, I think the information will be given through I think it already has been circulated, and rest of the information can be given through the WhatsApp group that has been created. And tomorrow's, I think it will start from 9:30. Just a minute, I will confirm once again. Yes, tomorrow's session will start at 9:30, and the first talk will be from Dr. Nitin Singh Singha from NIT Delhi, and the second session will be Dr. Pawan Kumar Verma from NIT Jalandhar. Thank you all. We'll meet tomorrow.